Hi everyone and welcome to today's video on logarithms. Hopefully the day's been a good one for you, or it's looking to be a good one for you. Now, I have literally just taught this to my year 11 group and wow, so much fun was had. Hopefully by the end of this, you'll also understand what I'm talking about. So by the end of the lesson, as I say above me, as is normal, hopefully I'll let you understand what logarithms are, what the general form of a logarithm is, and know how to use logarithm laws. Now, logarithms are something that if you said to your parents, oh, we did logs today, or logarithms, your parents would literally turn white and probably run from the room screaming. Now, why? Well, they would have had things when they were at school probably called log tables. I know my mum and dad did. And they were literally tables and tables and tables of logs because their calculators, they just didn't have them. They just couldn't work out these things. Not like your calculator today that can do everything, but including make the cup of tea. So logarithms was a thing of fear. Engineers used them a lot and sounded particularly technical using them. But anyway, I think they're really, really important, but we need to reference them with what we've previously done. Now, we've already been dealing with exponentials, and as I say here, one of the graphs we dealt with, for example, was y equals 2 to the power of x. Now, remember, with any graph that is exponential in nature, it curves up, and it goes through, unless it's translated or dilated, the value of, yes, 1 there. And generally speaking, whatever this value is here, this would be 1, 2. Yeah, why? Because when x is 1, 2 to the power of 1 is 2. So the general form was that curve. It went through 1, and life was good. Now, if I do the graph of y equals log 2 to the x. Now, don't get too excited at this moment about what this log 2 business means. I'll explain at the moment. But what we happen to notice is that this graph here is the inverse of that graph there, or vice versa. Now, again, going back to videos from my distant past, and like Scrooge, the Ghost of Christmas Past, we know that a inverse is basically where the line or the graph has been reflected in the line y equals x. So knowing that 2 to the power of x and log 2 to the power of x are inverses of each other is actually quite useful later on. And just to prove, for methods 3 and 4, what you'll see above me is a graph called y equals e to the power of x. Now, that's used a lot in methods 3 and 4. Again, it is a graph of an exponential function, but e here is actually a number, 2.718, and it goes on. And it's actually quite an important number for real-world applications. But this graph here is called y equals e to the power of x. And this graph here actually is y equals log base e of x. And again, using the language I say here, log base e of x. This thing here is called the base, and it can be all sorts of different numbers. Previously, a moment ago, as you can see as I'm scrolling above, we had log base 2. Log base 10 is really, really popular, and I'll talk about that in just a moment. But once again, what we notice is the graph of y equals e to the x and the graph of y equals log base e to the x are actually the inverses of each other. The dotted line here, once again, is y equals x. How do we know that they're inverse of each other? Well, because the x and y values are swapped over for all points along those graphs. So that's where they tie in with previous videos. But I suppose the question is, what do we use logarithms for? Now, I want to come up with an example. I want to grow something in my dungeon. In my basement. I don't have a dungeon. That would be weird as a teacher having a dungeon. What is this, Harry Potter? No, because that was the staircase. But anyway, what if I wanted to grow, I don't know, children? No. What if I wanted to grow zombies? Not so sure about that zombie thing. But let's say I want to grow something. So I wake up one morning and I go to my local place that grows things or sells things that grows. And down into my basement I go and I pour it into the primordial soup, otherwise known as the petri dish, and I just leave it. Now, I'm not very good at keeping track of things that I grow. If you were to see my garden, you'd see it was a barren wasteland of dead and dying plants. Not very green-fingered. So on day 1, I've decided I'm going to change a leaf. I'm going to go down and I'm going to pick something I'm going to watch these things grow. So day 1 here, I go down and 5 of these, I don't know, small children or zombies or whatever else have grown. And I'm like, yay, result. But yeah, I get a bit bored of these things. I'm like, yeah, okay, well, all right, done that now. So yeah, I'll check tomorrow. But you see, tomorrow never came in the sense of, well, it certainly wasn't tomorrow. I actually didn't go back down there until day 10. When strangely I had 4.5 of these things left. Now actually using children and zombies doesn't quite work. Zombies maybe, you could have half a zombie sort of crawling along the floor. And I'm like, oh, this is such a disaster. And I sort of forget about it for a while. And I go back on day 100. And yay! I've got 6 of these things. I don't quite know how this is all working. But imagining I keep going. And on day 1,000, like 3 and a bit years later. And then day 10,000 and day 100,000. I keep checking on these things. And I don't even want to think about how many years are in 100,000 days. But the point of it is, I am not necessarily great. Now, if I was to try and draw this graph, it would look dreadful. It would provide no real information. Why? Well, imagine this is my 0, and my biggest value here is 100,000. How on earth would you do an accurate scale for that? Well, that would be 50,000. Split that up into 1, 2, 3, 4. So this here would be 10,000. So my point number 1 would be sort of here. My 10 at 4.5 would be really, really close to it. My 100 would be still really, really close to it. By the time I get to 1,000, I may be sort of here. And suddenly I go to 10,000, which is sort of here, and all the way over here to 100,000. Well, all of my data is scrunched into one section of my graph, which makes absolutely no sense. How can I see if there's a pattern? How can I see if there's anything happening in this particular graph? Well, that's where we come up with a whole new numbering system. And what we actually do is we go, well, let's look at the idea of having powers or indices. And you're going to say, oh, what do you mean by powers or indices? Well, literally floaty numbers. Now, as it turns out, I know that the numbers 1, 10, 100, 1,000, 10,000, and 100,000 are all actually powers of 10. So this is actually 10 to the power of 0, 10 to the power of 1, 10 to the power of 2, power of 3, power of 4, and 10 to the power of 5. So if I could now create a number system which has this power notation, then wouldn't that be awesome? Well, my numbers would then become 10 to the power of 0, 10 to the power of 1, 10 to the power of 2, 10 to the power of 3, 10 to the power of 10. Well, that 0, 1, 2, 3, 4, and 5 means I can now actually draw a scale 1, 2, 3, 4, 5. I can have a much nicer scale with equally distanced divisors or points. So there would be my 0 and 1 and 2 and 3 and 4 and 5. So actually, that's where logarithms come from. We actually say, well, we can create a number system called logs that have a base. And by that we mean a 10 to the power of 1, 10 to the power of 2, 10 to the power of 3. So we could say, let this here be, sorry I've run out of room, log to the base of 10 of a number. So log base of 10 of 1 will be 0. We'll come back to that in a moment. Log base 10 of 10 would be 1. Log base 10 of 100 would be 2, and so it goes on. So log base 10 of 1,000 would be 3. And you may already start to see there's a bit of a pattern going on here. Well, now using this log system, I can now plot my data in a much, much nicer way. I'll create, what would that my first value be? So 0 would be, say, 5, and then 1 would be 4.5, and then 6, and then 9.8, and 14.6 and minus 7. My data actually has now a much, much nicer feel about it. I could probably do some sort of analysis, lines of best fits and what have you, but that's slightly outside this course. Now, bases are really important because they define the power system that you're dealing with. And again, not too deeply into all of this because it's slightly outside the course, but it's written as log base 10 of x. You can have other bases, log base 3 of x and log base 5 of x. And we've already seen one earlier, the log base e of x. So this value here is basically the thing that has a power. So this would have e to some sort of power. This would have 10 to some sort of power system. This would 3 to some sort of power system, and 5 to some sort of power system as well. So as I say here, the essence is that we are using logs to make really big numbers smaller and more manageable, particularly for graphing. It's used in chemistry, it's used in engineering, it's used in all sorts of things to make big numbers relatively small and easy to handle with. So logs are great. Once you know how to read a log, you are just in heaven. And what you need to remember is this log 3 of 9 is basically saying 3 to what power is 9? So 3 to what power is 9? Well, we know that 3 squared is 9, so the answer to that would be 2. Now, again, I can't stress enough. If you use the same language that I'm using to define these logarithms, you cannot go wrong. I genuinely mean you cannot go wrong. And I'll say it again. 3 to what power gives me 9? If I move on to my next example, log 4 of 64. So 4 to what power is 64? I can't obviously draw squares anymore, so maybe I shall change that to a value of x. Now, the way we're going to work that out is go, well, 4 4s are 16, and 16 times 4 just happens to be, I don't know, 64. So x in that situation would be 3. So log base 4 of 64 is 3, because 4 to the power of 3 is 64. One last example, log base 5 of 125 is 5. To what power? Gives me 125, and once again, it gives me 3. Textbooks like to be really generic and give you sort of formulas that you can work with, and so here is one of them. Log to the base a of x equals b, and I have written that a to the power of b equals x. That's nothing more than I was saying a moment ago. So if we had log 3, 9, there is my log of a to the power of x equals, well, they're saying b, so I said 3 to what power? So 3 to the power of b is equal to 9. And I've just rearranged things. I've just used a different letter. I have to say, I find this a little confusing. I don't really use it. It's great theory, but I always use that expression, what the base to what power is equal to the number that's beside it. Now, we in a previous lesson dealt with something called the index laws. And we've been using those since about year 8. Well, it just so happens there are logarithm laws as well, and I'm going to sort of talk to those a bit as we go. But just to give you an example, if we had x squared times x to the power of 3, hopefully everyone here would know that they were x to the power of 5. All you did was use a rule, a shortcut, something that we knew could make the process simpler, rather than writing out x times x times x times x times x, and knowing that there are 5 x's. Likewise, a to the power of 0 is 1, a to the power of b, all to the power of c is a to the power of bc. These rules, massively important, used never such a lot. And as it turns out, there are rules for logarithms as well. Now, although it looks like there's, 6 rules here, realistically there's only 3. Because a couple of the rules are actually the same. So these rules here are exactly the same. They're just written in a different way. So what I'm going to do is just go through them sort of with examples to show you how they're used. And fingers crossed, we'll come back to the rules in a moment. So we know that when logarithms are added together, when we have log a to the m plus log a to the n, then what you actually do is you multiply the values of m and n together with the same log. So that's the log of a of mn. All right, so the point of this is the bases have to be the same. In the same way as with indices, you could only use the rule when the x's were the same. Same with logarithms. So that means we have log 3 of 8 plus log 3 of 5. The logs are the same. Yep. So I get the log base 3 of 8 times 5, which gives me log base 3 of 40. Now you're going to turn around and go, whoa, I can't work that out in my head. And no, you're not supposed to. This is about simplifying, and evaluating comes a little bit later where you've got to find a specific value, because 3 to what power gives me 40? Well, not a whole number. So in that situation, I'd use my calculator. So when we add logs, we multiply the two values together. In this situation, 8 and 5. So in the same way as when you add logs, you multiply. When you subtract logs, guess what you do? Yep, you divide. So log base a of m minus log a of n is exactly the same as log to the base a of m over n. Now, I'm going to give you a bit of a sort of a warning here, because this is the one rule that's misused all the time. People make horrible mistakes, and I'll explain sort of later on why that is the case. But Are my bases here the same? Yes, log base 4, they're subtracted so I can use the rule. So log base 4 of 10 minus log base 4 of 5. Bases are the same. Tick, tick. Thank you very much. There's a subtract there. So I have the log base 4 of 10 over 5, which we can calculate quite simply as log base 2. Now, 4 to what power is 2? Now, actually, funnily enough, that one can be worked out. That one can be evaluated as a half. Now, you can say a half. Yep. Square root of 4 is 2. And the square root is the same as power of half, but we're getting way too excited with it. All I wanted to do was simplify it. Now another one, and this one is the most interesting law, and it's the one that's used in methods all the time, and in maths all the time. And what it basically says is that if you have log base a of m to the power of p, that's the same as p times the log a of m. Now that is freaking useful. Why? Because what it's saying is this floaty power here, when we take logs, can then be moved in front of my logarithm. And you're going to say, well, what's a practical example of that? Well, let's try this one. 3 to the power of p equals 8. Now, what if I wanted to find the value of p using logarithms, or I was asked to find out in terms of logs what it is? Well, anytime I see a floaty power now, I know that I can use logarithms to bring it down and stop it being a power. So I'm going to say log 3 to the p equals log of 8. Now you're going to say, hold on a moment, you've not put a base down. And actually, I don't need to, so long as I use the same bases. So that could be log base 10, it could be log base 8, it could be log base e. It doesn't actually matter so long as you take the same logs of either side. Now, using my rule here, I can now say, well, that's p times the log base 10 of 3 equals the log base 10 of 8. And how do I find p? I just divide both sides by the log base 10 of 3. Now, actually, here is where people make the most fundamentally crazy and scary mistake. They confuse this with that previous rule. And they'll say, oh, hold on a moment then. I can write that as the log base 10 of 8 on 3. And I'm going to say, please, please, please don't do that. That's not the rule. That's never been a rule. And hopefully, it never will be a rule. That is the simplified form. Now, looking at this particular example, you'll go, well, can I actually work that out? And I'll say, no, you still have to use your calculator because I don't know log base 10 or what power of 10 gives me 8. I'd still have to use a calculator. But the point of it is, later on in methods, you will start needing to use that rule to turn powers into in front of expressions. And this rule works in both ways, vice versa. And it's really important to know that. So this is an example of the rule that I'm going to undo. So 2 log base 3 of 4. If it's in front, I can move it to be the power. It works exactly the same. So that becomes log 3 of 4 squared. 4 squared gives me the log of 3 of 16. Again, can I simplify that any further? Probably not, because 3 to what power 16 doesn't actually work. So the great thing is the rule I just talked about a moment ago, which was log base a to the m to the power of p, looks like it has 2 rules, but in fact there is only one. So for example, if I have log base a of 1 over m, for example, we know that 1 over m can be written as m to the minus 1. So if I rewrite this now as log base a of m to the minus 1, do you see now how this links with OMG, that rule there? Because I now have m to a power, which means if I get rid of my brackets, just to make it clear, that power can move in front of my rule. So I get minus the log of a of m. Now again, the great thing about these rules is if you want to, you can just remember them all. I personally don't. I basically build them up from first principles, as it were. I think it means I'm not hopefully going to make a mistake in remembering them. So using this rule here, I have log base 10 of 1 over x becomes log base 10 of x to the minus 1. I've got x to some sort of power, so that becomes minus the log base 10 of x. Now you're going to try and say, is that simplified? It's written in a different way. Simplified, yeah, different story. But the great thing is this log stuff is awesome. And knowing these basic rules means you can actually manipulate all sorts of different logs. Our fifth example, and I promise we're coming to the end of this fairly soon, but we now have log 7, 1. And you're going to go, huh? Remember, this now means 7 to what power is equal to 1? Well, hopefully anything to the power of 0 is 1. So there we go. So actually, that value there is 0. And in fact, it doesn't actually matter if I had log base 10 of 1 or log base, I don't know, 100 of 1 or log base e of 1. Every single one of those is equal to 0. And in the same way, we can move this on. And if I say, well, what is log base x of x? Well, we actually know that the log a of a. Now say that out longhand. A to what power is a? Well, hopefully it's equal to 1. And the shortcut is, or the rule is, that when those two are the same, when the base and that number are the same, then it's actually equal to 1. So log base x of x, x to what power gives me x, must be equal to 1. So using this, we can go into sort of more complex examples. And I'm going to show you these just as sort of fillers to know how questions can try and trick you. So we have log 4 of 2x minus 1 equals 3. Now remember, we know that log the base of this is equal to 3. So we can rewrite that as 4 cubed is equal to that bracket. So we can rewrite that as 2x minus 1 is equal to 4 cubed, which is 4 times 4 times 4, which is 4 4s are 16, 32, 64. So 2x minus 1 is 64. 2x is 65. Or x becomes equals to 32.5. Do you see what happened there? We used the logs in a different way. We actually, in this situation, had to sort of reverse it and say, we know the power, we just don't know what that number is there. We know 4 to the power of 3 must be equal to our unknown number, which I effectively rewrote there. So again, what we can do forwards, we can do absolutely backwards. And the last question before I finish for today is solve for x the equation log 10x. So there's 3 log terms here that they're trying to trick us with. So the first thing I'm going to do is that log 10x I can't do anything with. Anytime I see a number in front of a logarithm, I know it's a power. They want me to move it back on top for that power. And I know the power of a half is a rational index. So that becomes log base 10 of 36 to the power of a half minus log base 10 of 3 squared. Now, do you notice they're all log base 10, so the chances I'm going to be able to simplify this. Log base 10 of x is equal to, well, that becomes the log base 10 of the square root of 36, because to the power of a half is equal to a square root, minus log base 10 of 9. Right. Log base 10 of x is equal to log base 10 of 6 minus the log base 10 of 9. Right, what do we do here now? Well, you might argue, well, we can get rid of all of the logs. No, you can't. That's where we're heading towards. But first things first, we have to deal with this. And when you take away logs, if you remember, you divide them. So log base 10 of x is equal to the log base 10 of 6 on 9. Now, I can simplify that down, but what I'm actually going to say is because I've got one term on the left-hand side and one term on the right-hand side, those logs now can effectively disappear. I can raise everything to the power of 10. That sort of, remember, makes sense because this is what we're dealing with. Logs are basics of powers. So what we're saying is, in this situation, that x becomes equal to 6 on 9 or equals 2 on 3. Now, this was a sort of running introduction at logarithms. We talked about how they're related to exponential graphs, i.e. their inverses. We've talked about the logarithm rules, and we've talked about why we use logs. It's been awesome. Thank you once again for dropping by now. Have you enjoyed the lesson? Hopefully, it would be awesome if you could tell people out there how much you've enjoyed it and that I'm here and that the videos are there for them to watch. If you haven't already, why don't you subscribe to my channel? It would help me enormously. And if you don't want to subscribe now, hey, leave it a while. But please, please, at some point, subscribe. Otherwise, there is a video over there loading for you on a very similar topic. You guys have a really good day, and I look forward to seeing you next time. Take care.